I'm reading this on behalf of Dr. Sehan Ersoy. I wanted to make an animation of a wing flapping mechanism. While doing some research about these kinds of mechanisms, I stumbled upon the treeswallowproject.com website. On the website, they mentioned that the feathers on a wing were opening during the upward stroke of the wing to reduce drag. This may be a well-known concept to some, but was completely new to me. The swallow picture you see here shows this phenomenon clearly, and I'd like to thank Chris Gates for giving me the permission to use this image in this animation. Please take a good look at this image as it plays a very important role in the following explanation. The wings on a bird are in fact a set of flaps which open when the wing rises and close when the wing descends. This means there is less pressure on the wing during the upward stroke than in the downward stroke. The quill or the shaft of a feather does not always lie in the center, but is often well to one side with a row of feathers arranged so that they overlap and turn somewhat on their shaft. I wanted to make this animation to show the flap action of feathers. At first I thought this would be an easy task. Since I had my wing flapping mechanism, as you see here, I thought the only change required was to add feathers onto it, and show how those feathers were acting during the upward stroke. Here's the animation of the wing flapping with flight feathers superimposed on it. I based my animation on the figures shown here from Lilienthal's book, Bird Flight, page 101. As you can see, flaps are opening on the upstroke to reduce the drag. The movement of the feather flapping is exaggerated to show you how the feathers operate. But there's a slight problem here. If you really look at the photo of the swallow, you can clearly see the gaps between the flight feathers. However, when viewing the bluebird shown in this mechanism, you cannot see between the feathers. Either I misinterpreted Lilienthal's drawing, or he overlooked some subtle errors in the artist's rendering of the condor wing arrangement. I did not see anything wrong with this arrangement before the animation, but the error manifested itself once I completed the animation. Apparently, something was not right here. However, the feathers could also be arranged differently than what was shown in the fictitious bluebird in this animation, and that is the case for all living birds, which are represented with the redbird animation here. Notice that now you can see in between the feathers. All the living birds' feathers flap mechanism works just like the redbird shown here. What is the difference between these two birds? Well, there are two major differences. The first difference is that the shaft of the feather, represented by green circles, is always away from the bird's body for the living redbird, and the opposite for the fictitious bluebird. The second difference is that the tip flight feather of the redbird is always fully visible if we look under the bird, and the other feathers always overlap one another. For the bluebird, the feather closest to the bird's body is fully visible, and the rest is overlapped. I call the redbird feather arrangement a positive arrangement, and the bluebird's a negative arrangement. Also, if the shaft of the feather is away from the bird, it will be called a positive feather and will be shown as a red feather. The bluebird's flight feather is such that the shaft of the feather is always closer to the bird's body. These kinds of feathers will be called negative feathers. It will be very clear soon why I use the term positive and negative for feathers and feather arrangements. If the feathers were acting as a flap, then why don't we see the birds in nature that are just like the bluebird? Since in both cases the flaps are opened in the upstroke, there should be a 50-50 chance for both the red and the bluebirds. However, we do not see birds like the bluebird in nature. Maybe it's because all birds, by luck, are descendant from one type of bird, and that's why we only see the birds like the red ones in nature. This would be a very simplistic explanation. Or maybe there is more to this than we imagined. As Lilienthal mentioned in his book, in nature, any design is not an accidental one. If nature selects one design over the other, then there must be a solid reason for that. Let's start digging into the subtle difference and see why nature selected the red bird over the blue one. As you can see from these animations, when the feathers are opened in the upstroke, the air is pushed toward under the bird's body for the red bird and away from the body for the blue bird. This is a vital difference, and here is why. Think for a moment that the blue bird is on the ground and a predator is approaching. The bird instinctively flaps its wings to take off. First, it pushes its wings downward and also pushes the air under its wings downward, and it gains slight altitude. But when the bird is in the upstroke, the motion of the wing creates a vacuum under the wing. Since the air under the wing has an outward inertia due to the previous downstroke, the bird does not have enough time to fill this gap. At the same time, the air passing between the feathers going outward, blocking some of the extra air coming toward under the wing. As a result, the bird will be sucked downward. This will nullify all the altitude gain obtained during the wing's downstroke, and because it did not get enough air under the wing, the next downstroke will be weaker. The bird will frantically flap its wings, and with each downstroke, it will go up slightly and fall down with each upstroke. So birds that are like the bluebird could only fly if they were to jump from a branch off of a tree or from a cliff. Taking off from the ground would be next to impossible for them. Now let's consider the redbird. When the wings are coming down, whatever happened with the bluebird will be repeated for the redbird as well. However, their upstroke is quite different from the bluebird's. While the wings are going up, the opening in the feather will push the air under the bird's body with a force that not only will it give it a supercharge the void with the fresh air from above, it will also give some upward force to the bird's body and keep it from falling downward. Also, the air coming around and under the bird toward the void will be assisted by the air coming through the feathers above. I use the term supercharge here because this is exactly what it is. The power used during the upstroke by the bird is converted, sending more air atoms downward. This has two effects. First, it gives an upward push to the bird, much like a Harrier jet. Second, it accumulates air under the wing for the next downward stroke, and the next downward stroke will take the bird higher. In short, for the redbird, there will be more air atoms to be pushed downward for each downstroke than the bluebird. Since it is supercharging air under its wings, the redbird will take off from the ground very efficiently. And due to the supercharging effect, we call the redbird's feather arrangement a positive arrangement. Feather arrangements also play a crucial role during cruising flight. As mentioned by Lilienthal, both birds, blue and red, will benefit from the opening of flaps because it will reduce the drag during the upstroke. Assuming that both birds are flying the same given speed during a cruising flight, one may assume that there are no differences between the two birds. Both birds will get fresh air under their wings due to their forward speed. However, there is a slight difference between the airflow generated by the upstroke of the wings. When the bluebird's feathers open during the upstroke, outward moving air pushes the tip of the feathers downward and tilts in such a way that it creates an out and downward air movement. However, with the redbird, this process will create a merging airflow as shown in the figure. This is a very important event. As we know, when an object moves through the air with speed, it creates a low pressure region behind it, which causes drag that will reduce the speed of the moving object. Therefore, the redbird's air movement will try to fill the gap behind the bird, reducing the drag. Since the bluebird's wings are pushing the air away from the body, it will not fill the gap behind it. This will cause considerable drag on the bird's movement. Also, the bluebird is trying to push the air outward into still air, which might show resistance to it and cause the bird to use more force and energy to push the air. On the other hand, the red bird's wings are pushing the air toward a cavity which needs the air, so that it can be filled. In short, the void behind the flying bird will reduce the drag, and as a result, energy consumption of upward moving wings will be reduced. The figure here shows a converging airflow for the red bird and diverging one for the bluebird. Is it a coincidence that these converging lines on the feather have the same direction and almost the same angle as the barbs on the feather? Is this a freak accident, or are the barbs assisting the airflow to be pushed toward the cavity behind the bird? I have a small hunch that this is the case. I thank Dr. Brett from the University of Montana, Division of Biological Sciences, for giving me permission to use this hummingbird picture in a wind tunnel. As you can see in this picture, the feathers open in the upward stroke and the airflow converges toward the back of the hummingbird. This figure shows 4 possible combinations of feather arrangements. The first, a positive feather arrangement with positive feather. The second, negative feather arrangement with negative feather. Third, a positive feather arrangement with a negative feather. And finally, negative feather arrangement with positive feather. Only the redbird has the capability of taking off of the ground and flying efficiently. The bluebird has the ability to glide, but would fly inefficiently. The other combinations are not suitable for flight and or gliding because the wing flaps would open during the downstroke. As you can see, having 2 birds identical in their looks, but with very different feather arrangements, leads to a different path in the evolution of birds. If in nature there were birds like the bluebird we showed here today, they could not compete with the redbirds. The redbird is a masterpiece of nature because nature threw everything in its arsenal to make the perfect flying machine. Thank you for visiting our YouTube channel. We would appreciate it if you rated our video, and please visit back soon.